Okay, I think I will go ahead and get started here. Hopefully we have everybody in attendance here. My name is Scott Wolf. I'm the Midwest Architectural Representative for WR Meadows. I want to thank everybody that's joined us this morning or early afternoon for this continuing education program. We will have, excuse me, we'll have some Q&A time at the conclusion of this, and if we certainly don't get to all the questions, we will collate all of the questions, and through email we will correspond with the answers. So do provide your email addresses if any questions don't get resolved. Pardon me. Excuse me. So with that, we're going to go ahead and get started. Want to conclude this at the top of the hour. Just get through a little bit of housekeeping here. Want to just give you a little backdrop of WR Meadows. The company is now 96 years old. We'll be celebrating our century mark here pretty soon. It's a privately held, family-run operation with 14 facilities in North America. We do have a recently acquired division which is our Blue Ridge fiberboard sound dampening products for multifamily development, as well as roof cover board type products. Just a quick image of our facilities in North America. Now, with that, we do market globally. So if anybody has any projects outside of the North American continent, around the world, certainly by all means get in touch with any of us manufacturers reps, and we'll be sure to walk you through the process. Some of our family of products, excuse me, include a huge complement of Division 3 construction liquids, concrete cures, hardeners, densifiers, patching mortars, anchoring epoxy resins, and certainly our Division 7 portfolio, which includes underslab vapor retarders, blindside waterproofing, cold fluid applied, hot fluid applied, and self-adhering sheet, and all of our air barrier products. We'll recap that just for 30 seconds at the end of this program. So anyway, with that, let's go ahead and get started. This is an AIA accredited program. Certificates will automatically be sent to each attendee, and certainly we'll look forward to answering questions at the conclusion. So today's program is on the basics of moisture movement through the building closure. This is sort of a basically essentially a 101 type program. And let's get started. So learning objectives today will be to identify pathways of moisture infiltration and the resulting consequences to the structural elements that we're trying to protect, of course. Examine optimal design and detailing to prevent moisture movement. This is the design and detailing is the proverbial end goal of any project. This is really where all of the unfortunate problems occur. So we really obviously want to get detailing done correctly, and certainly identified in the early design process, and of course specifications. We'll also provide solutions for the prevention of moisture, i.e. Look at some of the best products that are based for the best conditions, based on the project conditions. This is always something that I always try to look for early on the process when I'm contacted by an architect. You know, when is the project going to be constructed? And so we certainly want to be aware of that, and that certainly drives product decisions. So what is the building closure? Science of moisture control is not complete without considering the entire building envelope. This is not surprising. We can't lose sight of what I always like to refer to as all six sides of the box. The above grade walls are probably the most obvious and most often considered and looked at from a scrutinizing standpoint. Certainly the roofing is equally, if not the most important element, but we can't lose sight of the below grade elements, the foundations, and certainly the underslab conditions. And we'll examine the underslab conditions, underside of the sixth side of the box, below grade as well, because that's a big consideration. Excuse me. So moisture movement. This just reflects the process of how moisture finds its way to our structures. Certainly gravity. This is one of the words I tend to use a lot when reviewing drawings with architects. gravity is something that's always going to be working against us, and it certainly we can't lose sight of it. Capillarity or capillary water action is something that is also very, very important. Breaking capillary water action, as we'll discuss again, is very, very important. Getting that water away from the important life safety structural elements. And water vapor diffusion. Water vapor diffusion is simply a movement of water vapor in the form of a gas through an opaque material or materials, i.e. the structure, the four control layers, as we'll discuss. This is something that while I believe is very important, diffusion I think is probably lower down on the food chain of elements that are quote important. Not saying it's not important, but air transport is the mode of transfer that is and all building science people probably acknowledge this, is probably the most important thing that we have to be concerned about, and that's again alludes back to the whole detailing and getting all of these penetrations detailed correctly. Dew point is simply that phenomenon that occurs when the temperature drops, the humidity levels rise, and when those 2 points intersect, the humidity levels are usually at 100% RH, and that's where we have that thing called condensation. That generally is going to occur at, around, or generally within the primary thermal layer. In other words, the insulation layer of the building. So with that, and that's another aspect that's I don't want to go too deep in. We can certainly save that for there's another PowerPoint, permeable, non-permeable air barriers that we could set up for anyone that's interested. But it's something that I believe is probably less of a concern. I'm not saying it, again, it's not an absolute disregard it, but again, bulk air transport is where the majority of problems occur. So just something to keep in mind. So this just on that note, this really illustrates that bulk air movement. So moisture movement by air. Air movement accounts up to 90% of moisture intrusion into envelope materials. So this is again the biggest enemy that plagues buildings and building owners. Vapor diffusion, on the other hand, only accounts upwards of 30% moisture intrusion. So given, say, a 75-degree temperature differential between outside and inside, we can see that the vapor diffusion, that diffuse transfer of water vapor in the form of a gas going through an opaque material, and we'll just pick a piece of 4x8 gyp sheathing, for example, really does not constitute a whole lot of transfer. Here we're reflecting, 1/3 of a quart of water that could be accumulated through diffusion. That is probably, I would venture, easy enough to be accommodated by the building's interior mechanical equipment. In summertime, certainly, we're dehumidifying. In the wintertime, we're humidifying. So that can probably be taken up by our mechanical equipment. So if we take that same 4x8 sheet of gyp sheathing, put a little seemingly innocent 1 square inch hole in the center of that, giving it the same 75-degree temperature delta and 50% RH, 40% relative humidity, we can see that substantial amounts more of water can actually migrate through that wall system again. So it's all about the detailing. This is the point I always try to make clear in these programs. So air leakage pathways. There are almost innumerable number of ways that air can enter the structure. Air moves through cracks, gaps, the wall to roof, wall to foundation connections, mechanical, electrical piping, MEP penetrations, window openings are all, some of the examples of how air enters our structure, and hence the reason why those areas must be properly flashed and detailed to meet, frankly, airtight and watertight. Without that, we can have uncontrolled air leakage getting into our interstitial space in between our framing. If our insulation happens to be bad insulation, that can actually introduce wind washing, which degrades thermal performance. And then, of course, obviously, if water gets in or moisture gets in, that further degrades bad insulation in particular, and perhaps maybe to a lesser extent, rigid insulation. But ASHRAE has an article. It's a dated article, but it illustrates that the actual R value of insulation with these maladies can be reduced upwards of 80%. So if we have R19 or R21 R22 bats, the reality is that insulation might be with these types of problems could be as little as R7 or 8 or 9, given poor envelope retention. So why moisture protection systems? Moisture intrusion damages equipment, interior finishes, excuse me, and protection against moisture increases the life cycle of structure. This is not surprising. It improves occupant health, safety. It helps to mitigate mold, and owner occupancy. Excuse me. Comfort makes individuals more productive if we're talking about a commercial structure here. And of course, mechanical equipment energy costs can be affected or reduced if we have a properly installed and certainly specified detailed envelope system, waterproofing air barriers. Excuse me. So the water control layer is basically that's going to be an air barrier, that's going to be a roofing system, that's going to be a foundation waterproofing. And the first order of business always is to ensure that the water is shed away from the structure. I see this all too often. I've personal experience with it from my personal residence, and we'll see how that is so here in just a second. But drainage is really part and parcel. Something that should always ideally be included with a waterproofing system. There are some above grade drainage features for air barriers. I have sort of my candid thoughts on that, but we can save that for maybe a detailing air barrier PowerPoint at some point. But drainage is always a good idea because it breaks that capillary water action that inevitably the structure is going to see. Number two, it's also going to route that water away from the structure or into a drain tile system. And C, it can certainly serve as a protection layer. Protecting the membranes that we apply to our structures is very, very important. So all it takes on the note of deflection, all it takes is just a little bit of grade slope towards a structure. This is an example of perhaps, I'm guessing, maybe 0.5%, maybe 1% grade slope towards this house here. This was the result of a 7-inch rainfall in 6 hours. Yes, we get those. I'm sure everybody's likely experienced something along these lines, but it just takes a little bit of grade slope towards a structure to create a serious problem with water immediately right up against the foundation. So we always want to have the grade sloped away from the structure and ideally routed into some type of drain tile system. And always important, I almost feel like I do this on a daily basis, but always have the water either daylighted or routed into some type of drainage system, whether it's a sump pit, or some type of large body. Ideally, get the water away from the structure. So the 4 control layers. This basically is the air control layer, stopping bulk air leakage, water control layer, water vapor control, and thermal layer. Often, in some cases, these can be all contained in one material. At least the first 3 can. There are products out there, i.e. rigid insulation, that can act as all 4 control layers. If we're looking at these 3 examples here, above grade walls, of course, the flow through assembly is that quote old fashioned wall where we simply have essentially a building paper or a vapor permeable air barrier, more properly referred to as on the cold and winter side of the insulation. And if it's in the project happens in zone 5 or higher, the chapter 14 of our code dictates that we have to have a class 1 or class 2 vapor retarder on the warm and winter side of that primary thermal layer. So this is allowing any water vapor in the wall to have a way and a means of egress, i.e. the vapor permeable on the exterior side. All four control layers on the exterior side is the middle detail, where we basically eliminate bad insulation between our framing if our wall happens to be composed of framing, and just put all of the rigid insulation on the outboard side of the exterior wall. In this example, this is really what's often referred to as, quote, the perfect wall. There's a great article I always recommend, titled "Understanding Vapor Barriers." If you just do an internet search on that, capitalize each, usually the first item that comes up. It's free for download, but that's where these are captioned from. This is considered the perfect wall. However, it is far and away the most expensive wall to build, because if we put all the insulation on the exterior side, we have to have obviously a bigger foundation, longer tie mechanisms for the cladding system. But why we refer to this as the perfect wall, the article by the same author titled "The Perfect Wall," is that this basically keeps the entire structural element, the most critical item on a building, of course, above the dew point. So really the entire structural wall is kept at or near the same interior conditioned environment via the mechanical systems. So this is a great wall, and in my humble opinion, it tends to take out the guesswork of what type of air barrier to use as far as permeable and non-permeable. If anybody can see the image here, it does suggest a class 1 vapor retarder type air barrier. So it's basically marrying that with basically a class 2 vapor retarding insulation. So we basically now have all four control layers, four basically non-permeable control layers on the exterior side of the building. So great article if you get a chance to look at it. The third detail is the combined or hybrid assembly, and this basically may allow for the wall system to get a little bit reduced in its overall footprint by combining both exterior continuous insulation and bad insulation, where we could have some of the thermal air between the framing. So anyway, enough on the control layers. Air leakage. In theory, it's easily dealt with. Stopping the airflow is obviously the biggest goal, as I mentioned earlier, and I'll continue to hammer that point home. Some cracks, and in reality, it's probably easier said than done. I always discuss in many of these PowerPoints that considering the ease of which air barriers, and for that matter, foundation waterproofing systems can be installed, the better the quality, the deliverable. The more complex the geometries we have, the more difficult it is to achieve a plane of air, complete air tightness. The image in the lower left, or in the bottom center of the screen here, was sent to me by a specifier, and asked, what type of air barrier should I use? And I honestly said I don't really have anything for him, because it's obvious. There are holes in the courses of block. The mortar joints are pooching out from the plane of the block. They're at the rough opening. The block is standing proud of the majority other sections of the wall. Some of them aren't even in alignment with the correct plane. It would probably be easier to just tear it out and start over, rather than knocking the mortar joints flush, and then filling those holes, and then possibly using a liquid flashing. It would be a lot of remediation, certainly not impossible, but very expensive and time consuming, and frankly, very difficult. So again, try to consider the conditions with which the membranes are being installed. So an effective air barrier should be obviously strong, capable of withstanding positive and negative wind, fan or stack pressures, or wind forces imposed on a building. They need to be durable. They need to certainly last the service life of the building. And that's probably, I want to say, potentially a given, because most all air barriers are really going to be behind a layer of exterior continuous insulation. So we've taken out the biggest enemies, UV and thermal shock or thermal cycling. Continuous again, this alludes back to making sure that the air barrier system is connecting with all of the penetrations, the window openings, the transitions to the roof, transitions to the foundation, excuse me, and resilient. Most air barriers, and this is where most air barriers really comply. Well, most all air barriers are resilient, meaning that they have a fair amount or pretty decent levels of elongation and tensile. They can move a little bit with the structure. Certainly, they do have their limitations to how much extension that they can tolerate. Types of air barrier materials really fall into the long-standing, probably 50 plus years, mechanically fastened, the spun bonded polyolefin building wraps. And these are typically, in pretty much every case, going to be vapor permeable. There are also self-adhering sheet air barriers, both available in vapor permeable and vapor retarding. Spray foam, specifically closed cell spray foam, foamed in place insulation, the 07-2119, if I remember correctly. These are also qualified by the IECC, as all of these products are, the International Energy Conservation Code, as being an air barrier. I'm a big proponent for spray foam because I know it to be compatible with pretty much any barrier. The only exceptions I would probably say would be silicone type air barriers and possibly vapor permeable self-adhering sheet air barriers. So check with manufacturers, but pretty much anything else it will adhere to. Fluid applied air barriers, these are products that have been around, I believe, conceivably almost 50 years. They've been in existence. They really haven't come to prominence until probably the last 25 years or so. These are both obviously available vapor permeable. There are different types, acrylics, STPEs, silicone are probably the three main categories, but all of these products have to be air resistant based on the standard that we reference here, which is typically found in the specification E2178. It just simply dictates that the material can't allow any more than 1.57 pounds per square foot of air permeance through the requisite material. There are various types, again, self-adhering sheets. They're available permeable and non-permeable, fluid applied, make for very quick going. I find that a lot of specifiers in Canada tend to prefer the self-adhering sheets. This is just from many years at this. They cite colder weather capabilities as why they tend to prefer this. I tend to disagree because plenty of fluid applied air barriers do have low temperature capability, easily to 20 degrees, some of them even lower than that. Now, we cite air temperature and substrate temperature below freezing, but it's always advised, and frankly, us manufacturers probably need a little bit better marketing on this aspect, that the material has to be kept at or near close to room temperature until just prior to application. That applies certainly to self-adhering sheets as well as fluid applied membranes. And foamed in place insulation, one of the reasons I like it so is it eliminates having to tape any joints. It conforms to irregular shapes, and again, I know it to be compatible with STPE, water-based acrylics, 40 mil self-adhering sheet air barriers. It to me is the ultimate wall. If we have a rigid foam insulation bonded to an elastomeric 40 mil rubberized asphalt, that to me is really the ultimate wall. But that's of course a pretty expensive wall to build. And then of course there are these mechanically fastened board stock insulations, which again are recognized by the IECC as qualified as being an air barrier. So they resist air based on that E2178 standard. So same with the mechanically fastened. Now, the points exceptions I would take to rigid board stock insulation, and for that matter, using spray foam as a standalone without any other elastomeric membrane behind it, is that they have virtually negligible elongation or tensile properties. If we consider a steel framed building, a mid-rise or even a high-rise that's subject to a lot of wind forces, frankly, all three modes of axes of movement, X, Y, and Z axis movement, this foam doesn't like to move. I used to be in the gypsum world, and I've actually seen gypsum panels fracture in the field areas of the panel, the 4x8 sheets. So if we do not have an elastomeric membrane behind, say, a rigid piece of insulation, and this is now acting as all four control layers. We've basically compromised our entire envelope. But if the rigid insulation does fracture, but we do have a membrane behind it, we've got still a plane of air tightness, but something that's going to have, 400 to 800% elongation that can potentially accommodate some of those differential movements buildings are inevitably subject to. So this is the kitschy slide we have here. Which of these is not an air bearing material? The reality is that all of these materials are qualified as an air barrier. Even Jif peanut butter. If anybody's familiar with the Air Barrier Association of America, Laverne Daglish, who is the principal there, actually did do an air leakage test based on that referenced E2178 standard, and found that yes, in fact, it did not allow any more air leakage than dictated by that standard. So, but cast in place concrete, core filled or grouted CMU, are all is an air barrier. Same with gypsum panel products. Even plywood and OSB are qualified as air barriers, but they don't have the elongation or the tensile properties of the membranes that we were talking about. So now we get to the below grade aspects. We have to ask the questions. Do we need damp proofing, waterproofing, vapor proofing, drainage? That all, again, based on the building, the expected use of the building, owner's expectations. Damp proofing is probably the least common denominator. Water vapor proofing. Vapor proofing, we might use below grade underneath.
Scott.
This is say a damp proofing. What do the geotech soil test reports indicate? If our foundations are going to be at 17 feet below grade, and the geotech indicates that groundwater is at say 25 feet, then that's probably a good indicator. If the site happens to be on a high elevation relative to surrounding other areas, this is probably a good sign. Okay. Thank you, Riley. Appreciate it. Site drainage. Site drainage, again, sound is working. Very good. Thank you. These systems. I'm not a technical guy, so, or at least IT wise anyway. So site drainage is also very, very important. We want to make sure that water is obviously getting away from the structure. Compromised irrigation systems, structural cracks, improper waterproofing details. The more complete the details, obviously, is going to help those installing the products. We don't want to leave anything to chance. And again, great. Riley?
Yeah, I just got you back. What happened?
I don't know. I'm just sliding, going through these things. I don't know what's going on. So
you wiggling the router wire, Scott?
I've not touched anything, and I'm using my mouse because I lost my Slide Advance device. So I will try to be very ginger here. My apologies to all on the call here. So let's move along here. Lost enough time. So this nothing to see here. This is another example of how moisture enters a structure. This is my personal domicile, and be wary of individuals referring to them as home inspectors, because the home inspector did not catch this. Yes, water was dumping right on my gas meter, and yes, it has been remedied by yours truly. So nothing to see here. How does moisture enter structure? The seeming innumerable points of entry or exit. When reviewing wall to roof connections, I always try to make abundantly clear that that the wall to roof connection is made via a 100% fully adhered connection. Okay. And this image here is probably about 5 minutes from my home, but I all too often see single ply roofing membranes overlapping the air barrier and just simply mechanically fastened to the air barrier. In heat dominated climates, climate zones 5 and higher, typically warm, moist interior air in the wintertime scenario, because we're humidifying, will rise and find its way to the point of least resistance which is potentially at the parapet condition. And of course, this is the ugly result, is we can have substantial amounts of water finding its way to the outside. So high temperature is always going to seek low temperature. Higher humidities always seek lower humidity. They always want to seek their equilibrium. So this is why we want to make sure that we get all of these connecting points fully adhered. And there are compatible solutions to make this connection in the world of air barriers. Is a adhering butyl transition membrane. Why I bring this up is that butyl is not negatively affected by the high solvent primer adhesives commonly used by single ply roofing manufacturers. There are also other products out there. I can't really cite specific brand names, but there's some solutions I can certainly talk about offline here. So how does moisture under the underslab? I'm having trouble with this little thing here. So we have to also consider that the ground, the soil, will always constitute a nearly 100% RH condition. And again, for a below grade portion of a structure that is conditioned, humidified or dehumidified, we have to consider the temperature delta and the vapor pressure delta between the two environments. So if that's the case, again, we may want to consider an underslab vapor retarder, or for that matter, an underslab blindside waterproofing altogether, which can also help mitigate water vapor transfer. So concrete is not vapor impermeable, thus the need for underslab protection. So, and concrete also has a lot of capillaries, which is what the mode of transfer that moisture will find its way into a structure. Acceptable substrates: cast in place concrete, of course, precast concrete panels, hollow core concrete planks, concrete block, shotcrete, plywood, OSB are all acceptable substrates for receiving membranes. Just a weird side note: if anybody's specifying hot applied rubberized asphalt on precast concrete planks or hollow core, I think there's a generic term, Spancrete, or maybe that's a proprietary name. Forgive me. Those substrates have to be basically scarified to a concrete surface profile of 3 or better to provide good mechanical bonds. So there are some subtleties. So always check with the manufacturer's technical reps when specifying these types of systems. Masonry joints are to be struck flush. I used to see this a lot in specifications, but lately it seems to be evaporated from specifications. Very, very important. We don't want to have tooled joints. Our membranes applied on joints that have a tooled concave profile? Yes, they are. But that makes the membrane a little bit more challenging, makes it more challenging to get the membrane continuous wherever we have any type of peaks in the substrate. So get rid of the fins, the pock marks, any of those things, in the substrate, so that we have a flat, true surface. Seems logical enough, I guess. Other factors: water penetration, permeability. A measure of the ease with which fluids or gases flow through material, through pockets and voids, and porosity, the volume ratio of openings to the total volume of material. And water to cement ratio is that which really drives the porosity of concrete. Lower water to cement ratio will typically result in a more dense and structurally strong concrete. Proper concrete consolidation is something that I also really try to make folks aware of, because if we don't properly vibrate the concrete, then these pock marks and voids. There's a project in Chicago that completed a handful of years ago. Probably at about a 3-story concrete podium below. It was about a $980 million very high-end condominium building, but the 3-story parking above grade had a lot of the cream of the concrete float to the surface, resulting in a lot of the forms. It's failing. And to me, that the air barrier contractor just simply sprayed applied over that scale. Protection, obviously damage to the interior, poor indoor environmental, and once concrete once they apply the concrete, and that creates the whole spalling condition, and then that further exacerbates and creates the domino effect of increased water infiltration, and the results are obviously quite disastrous. So now that we see the negative of moisture infiltration, the waterproofing the system needs to be made. So we need to differentiate between damp proofing or waterproofing, or consider vapor proofing for, again, as mentioned, interior sensitive flooring finishes. Anticipate the time of year for installation. Again, some materials can be installed well below freezing. We also have to consider, whether or not a construction crew will be able to would be interested in installing those conditions. Geographical location, local codes, owner expectations, and certainly the warranty. These are all questions we need to ask prior to deciding what type of material. So damp proofing, as I mentioned earlier, is really the lowest common denominator for protection of a structure. It's typically it's a material used in the absence of hydrostatic pressure. So hydrostatic pressure is basically that which is going to be driven by high groundwater levels. Waterproofing, on the other hand, is a water-resistant material used in the presence of hydrostatic pressure. So if our foundation, again, I'll use my example, our foundation is at 17 feet below grade, groundwater levels are found at, say, 8 feet below grade, then most definitely we want to protect the entire structure, including the underslab conditions. So in the presence of positive hydrostatic pressure, yeah, we basically to bathtub the structure. Waterproofing material types include self-adhering sheet waterproofing. These are nothing new to the industry. They were developed roughly 51 years ago. The 60 mil self-adhering sheet waterproofing, that which specify in 07-13-26. Fluid applied membranes are hot fluid applied SPS rubberized asphalt, cold fluid applied. These are commonly single component polyurethane asphalt or polyether asphalt based cold fluid applied membranes. And then PMMA and PUMA. These are really listed in that category from least to most expensive from that perspective. And then cementitious membranes. Not really a new product category, but these are tremendous products used for both positive and negative side waterproofing applications. Just a quick side note on cementitious waterproofing membranes. If they're used, always check with the manufacturer. It's ideally recommended that the cementitious waterproofing membrane is specified and used with the same fluid applied or self-adhering sheet membranes, or excuse me, just the fluid applied membranes. So check for the compatibility there, because I ran into a situation where another crystalline type waterproofing was used, and there was a compatibility problem there. So there may be a little bit of a hiccup there. So, and then the blind side under slab systems, the pre-applied sheet are used again in high hydrostatic water conditions. We had a project on Biscayne Bay that had it 60 feet below grade right there on the bay. So obviously we completely bathtub that entire structure. It was a giant aircraft assembly facility. So self-adhering sheet waterproofing membranes are probably, I believe, probably far and away the most commonly used waterproofing. It doesn't involve nearly 400-degree asphalt. We can use it for both horizontal and vertical. This is a 60 mil self-adhering sheet that is a 4 mil high density polyethylene carrier film bonded to 56 mils of rubberized asphalt. Factory controlled thickness. We don't have to get our wet mill gauges out, so we know what we're getting every time. It adheres to most structural substrates, including even insulated concrete forms. That we have to certainly be aware that we have to use a water-based primer, because self-adhering sheet membranes do require primer. So, but in horizontal application, this is my personal preference, is I always prefer to have 2 plies, just simply due to that thing I mentioned earlier called gravity. items get dropped, especially during the assembly. Having a second layer provides an added layer of robust, redundant belt and suspenders, if you will, protection. We'll always have to have some form of protection. If it's a concrete split slab, then that's basically our protection layer. But during the backfill, we want to cover this up either with a drain board or some type of asphaltic protection layer. Fluid applied membranes, again, hot, cold, and these resin type of PMMAs from least to most expensive. Hot fluid applied is far and away probably the most commonly used for plaza decks, green roofing, split slab concrete applications. And again, it's going to be probably the most price effective, i.e. the lowest cost of these three options from a materials cost standpoint. The cold fluid applied, the labor is exactly the same. It's often a squeegee type material. There are some spray applied type materials. In a high build, we still use the same reinforcing fabric we do for hot applied. And then the PMMAs, which are really not a new technology. They've been around for probably about 50 years. The PUMAs is basically PMMA with added polyurethane, just gives it better flexibility at colder temperatures. These are all terminated, and what's really nice about them of our detail work with the PMMAs ahead of schedule, and then just bring in the kettle and do all our waterproofing on the flat, do the flat work once all of our detailing has been accomplished. The PMMAs do make quick work of pipe penetrations. Some of these grocery stores where we have a grocery store at street level and parking above it. We had one such project where we had probably about 40 pipe penetrations coming through the split slab, and so that's where this PMMA or PUMA flashing makes great sense. So I hope my audio is still working. Hot applied rubberized asphalt, again, considered the most cost effective. Nearly limitless minimum application temperature. Most manufacturers will cite 0 degrees. One such manufacturer cites no limit. I was privy to a project in Eagan, Minnesota in 2004, where in addition to a pre-existing insurance company had to require the installers to install at night. They had about 90,000 square feet of waterproofing to get down. This was in the first February that year. The application went off without any problems. I believe that nighttime temps were reported to have dipped down to about minus 15 degrees. But I could think of worse things to be doing, slinging 400-degree asphalt in that type of condition. But the caveats to hot applied rubberized asphalt is ideally 28-day cure time. Manufacturers generally accept 14 days minimum. This is just how it is. Concrete has a lot of moisture in it. If our concrete is lightweight structural concrete, and I emphasize structural, the minimum cure time is 60 days. Lightweight structural concrete is hydrated for several days before it's poured and uses a slightly different aggregate. So hence the reason the bound moisture takes that much longer to basically be released. This can be applied to gypsum roof cover boards, plywood, OSB, but that adds another layer of detailing. All of the joints have to be reinforced, of course. And in a hot applied rubberized asphalt, the spec should always require authorized installers recognized by the manufacturer. Cover those other points. Cold fluid applied, most often are going to be a single component. However, there are some plural component products out there. These are generally limited to about maybe 30, 32 degrees ambient and substrate. Check with manufacturers. And some of these actually incorporate sile terminated polyether, which make them a little bit more compatible with a wider variety of materials. And we can apply a single ply or 2-ply reinforced 60 mil plus 60 mils with reinforcing fabric. One of their biggest benefits, however, is application to green concrete. The moisture curing aspect of these cold fluid applied membranes actually benefit from and frankly require atmospheric moisture and substrate moisture to go through their curing process. So we say green concrete. Depending on some manufacturers, they might cite 24 hours, 48 hours. I generally like to use a 72 hours minimum after the removal of forms, but that obviously is a boon to production teams to get the building watertight in pretty quick order. So, and again, they are also generally compatible with these resin type of waterproofings. So yeah, in a horizontal application, if we have a panelized deck system like we see here, we have to reinforce all of those joints. So that obviously adds another layer. Compare that to a cast in place concrete deck. But it's, if it's a cold flute applied, it's 60 mils down. Actually, this looks like hot applied rubberized asphalt. So we typically go 90 mils, reinforcing fabric, 125 mils, and then roll out the protection layers. So, but again, we always ideally want to have contractors installing these types of systems recognized or authorized by the manufacturer. Blindside or under slab systems used for deep foundations. These are bonded to the concrete, so these become basically part of the concrete. They come in either a mechanically bonded type of membrane or a chemical bonded, and there are some companies that actually have chemical and mechanical bonding. These are used often in zero lot line conditions. Again, I talk about deep excavations, or heavily densely populated urban centers, Chicago, Philadelphia, New York, just anywhere we have very dense populations. We have to basically protect all sides of the structure. And certainly they are used up against lagging systems, sheet pile, soldier pile, wood lagging. But the sheet pile and the soldier piles, do require infill preparatory work done ahead of time. We basically, again, need to have a flat, uniform surface to apply these systems to before we start installing our blind side, because we cannot introduce it into those recesses in a sheet pile, because it's not a flat, true flush plane. Membrane protection and drainage boards, again, I can't express this enough. It is required. Membranes have to be protected, again, from either backfilling operations, trades walking on the horizontal. They're really technically not waterproofing, because the waterproofing is underneath it. As their name implies, they are just simply protection courses or protection layers to protect the softer, more easily damaged waterproofing membranes until the rest of the assembly is put together. Prefabricated drainage layers. These, again, serve several functions to protect the membrane, reduce hydrostatic pressure, and route the water away from the structure. Always run the type of drain board past the structural team on the project, because these come in markedly different compressive strengths and drainage capability. We don't really know what the drainage requirements are. They might vary anywhere from, say, 12 gallons per minute or up to 17 gallons per minute for the core in between the drain board. And then the fabric also has a certain amount of flow through based on the sieve size or the opening size of the non-woven fabrics or woven fabrics, depending on the application, but most often the non-woven fabric. Cementitious and crystalline type waterproofings. These are, the crystalline are either found in admixture or topically applied. And then there are flexible cementitious types, which are essentially a film forming type of membrane. What these do is they basically combine with the free lime within the pre-existing concrete and initiate a renewed crystalline growth, because as I mentioned earlier, concrete has under high magnification have a lot of has a lot of pores, and that's what obviously allows water vapor or water to migrate again wherever we have a sizable differential temperature differential or a vapor pressure delta between two sides. So the Achilles heel to these types of systems is they obviously cannot be applied to expansion joints. They have limited elongation. If we have larger cracks, this is obviously not going to magically fill that in. And surface preparation is very, very important for the flexible cementitious or the non-flexible crystalline type systems. we typically require or specify minimum 5,000 psi to basically score the surface or open it up. Again, for the International Concrete Restoration Institute, we have to have a CSP of minimum of 3 to provide a good mechanical bond of these systems as they're being applied. I think I'm probably about getting close to running out of time here. So uses for cementitious waterproofing, horizontal, vertical foundations, municipal water systems, wastewater containment, potable water tanks. Some of these systems are NSF 61 compliant. Elevator shafts, elevator pits. Probably one of the bigger uses are below grade parking structures. If it's a pre-existing parking structure, it's experiencing efflorescing or stalactites for that matter, building up along the vertical faces of a garage retaining wall. These are great applications. Probably far and away the biggest use for these are wastewater containment. They do have chemical resistant versions, basement swimming pools, and certainly we specify these in a number of cases as a backup belt suspenders in addition to a self-adhering sheet or liquid applied or blindside type waterproofing systems. And again, we talked about properly prepared surface. This is an example in the upper left-hand corner of a CSP3. It does require high pressure water to achieve this. Mechanical braiding, interestingly, is not generally acceptable by the manufacturers. So, if it's a pre-existing building and it's below grade and it doesn't affect the interior occupants in other areas of the building, this might be a possibility. But this is something I always bring up early on if somebody's considering this, is this high pressure water opening up of the concrete to receive the crystalline. So other causes of envelope failure, obviously once water gets in, adhesive failure of VCT type flooring finishes, and then the aforementioned, previously mentioned concrete oxidation. This creates spalling. Epoxy floor finishes can start delaminating where we have high hydrostatic pressure. We didn't have an underslab waterproofing. That water is always going to try to seek the lower vapor pressure. So higher pressure seeks lower pressure. So just some of the aspects here. Low grade vapor retarders. These are generally used for the least expensive type system. But these are used for, again, interior sensitive floor finishes, but they can also be used to mitigate, noxious gases like radon. For building over a BTEX chemical brownfield site, we definitely want to have a vapor retarder. They're the least expensive of all options, but there are some systems, some waterproofing systems that have extremely low water vapor permeance and also are proven to be barriers to these aforementioned chemicals or radon. So check with manufacturers to, that might, if we need waterproofing and protection from passage of these types of gases, this would be certainly an option. Oops, I lost my slide here. So, okay. All right, so vapor barrier versus vapor retardant. Just a little bit of housekeeping on this note here. ASTM recognized the term vapor barrier and vapor retarder as being equivalent. In reality, is not correct. No material is a true barrier given enough pressure, and all materials can and will experience some diffusion of water vapor or any of these gases that we might experience trying to get into our structures. So currently ASTM E1745 and 1643 only use the term retarder, and that's really correct. If anybody is a code weirdo like me, check chapter 2 of the IBC or the code under the V section for vapor retarders, because it breaks retarders into 3 categories: class 1, class 2, and class 3. Class 1 is the most restrictive. Class 1 and class 2, frankly, are recognized in chapter 14 of the code as that which we've been calling a, quote, vapor barrier behind our warm and winter side of our insulations. So ACI 302.1 defines vapor retarders as those that have a water vapor permeance less than 1/10 of 1 perm. And that's really the same definition as the code definition of a class 1 vapor retarder in chapter 2. And ACI 302.1 R18 also recommends vapor retarders for sensitive interior floors. So thank you. Yeah, no, appreciate it. So about out of time here. I do with all these technical difficulties, but I'm just going to quickly roll through some of the images here of a below grade vapor retarder. Get those penetrations done correctly. And when specifying these, just do understand that we have several options. We have ASTM 1993, the standard spec for bituminous water vapor retarders, and then E1745, which is that for plastic water vapor retarders. Try not to intermix, bituminous ones and then specify only E1745 and the reverse, vice versa. So just know that there are two different categories of these. We often see plastic vapor retarders in a E1993 spec. So just know that there are two different standards for two different types of systems here. So site preparation and installation, it's always good to include these. They're not necessarily required by the manufacturers of these types of products, but it's always good to have them in the specification, just really to hold the installers accountable to getting things done correctly here. So, and then to kind of close out here, water vapor material and property standards. These are really what we typically see in a waterproofing specification. I'll let everybody take their phones and snap a quick picture of this rather than me reading them all off here. So, and then material selection, what type of substrate, high or low surface porosity, time of year. Ensure that listed manufacturers provide all the requisite accessories. Us lowly manufacturers reps constantly get hit by the GC allowing the installer to cherry pick, the through wall flashing from one manufacturer and then membrane air barrier from another manufacturer. Then we get in that whole compatibility thing, and then we have to write a letter at the worst time of the project, which is when things are underway. So, and specify materials of the same composition and properties and performance. This is also something that we do more in detail in our detailing air barrier PowerPoints. So, pre-construction meetings are always a good way to make sure that everybody's on the same page, and we make sure that all of our connections are made airtight, watertight, and vapor tight, and fully adhered. I can't stress that enough. So anyway, I'm about out of time here, and I'm going to stop it right here and open the floor up to questions. But if none, I want to thank everybody and for all of their patience through all of our technical mishaps here. But hope this was helpful. If I can be of help, my email address is here, swolf@wrmetals.com. Please feel free to reach me directly or send any inquiries to info@wrmetals.com. And this is a quick snapshot of all of our waterproofing and air barrier products. And if anybody's interested, we have these quick reference organizers for publicly bid project specifications. It's a Meadows Division 7 product organizer. So it lists all the products by spec number and title. The recommended Meadows product in yellow highlight correspond to the competing brands in light blue font, listing the manufacturer's name and their individual product name. So there at least 3 products are listed here, again, for publicly bid projects. So I'm happy to send this over. So let us know if anybody's interested. With that, thank you.